We'll start now. So in the previous sessions of analog and digital electronics, we have gone through the internal block diagram of operational amplifier. Okay. So what we have seen in this particular case is we will be available with total 4 stages. The first stage is known as input stage, where we have dual input balanced output supply, differential amplifier, right, as our first input. Then we have the intermediate stage, which is nothing but the dual input single ended output differential amplifier. Okay, then the output of this amplifier, we are providing it to the level shifting stage, okay, which is nothing but one emitter follower circuit. And then the output of this emitter follower circuit is again fed back to push pull complementary amplifier, and it will give us some output. Okay, so we will providing in 2 input signals and we will get some output which is in multiples of the gain. Okay, so depends on output voltage, depends on the value of the voltage gain provided by a typical amplifier. Okay, and to get the desired gain, what we are doing, we are using here at the second stage the multi-stage amplifiers are used to get the desired gain. Okay, then we have gone through some ideal operational amplifier characteristics. Okay, so we have seen the ideal values of different characteristics like input impedance, output impedance, bandwidth, what should be the value of power supply rejection ratio, what should be the value of common mode rejection ratio, etc. And then we have gone through the voltage transfer curve. Just a minute. ત્યાં એડમિનમાં જશો ને, એડમિનમાં ઉપર વિજયભાઈને મળવાનું. હા, મેઇન ઓફિસમાં સ્ટોરમાં વિજયભાઈ. Okay, so we have seen the 2 kinds of voltage transfer curve. One was the for the ideal amplifier and another one for the practical amplifier. Now what we have seen in case of ideal amplifier, we have seen that we will be available with a vertical line up to the maximum supply voltage. After that we will get the constant output, okay, which is saturated output. So plus Vset and negative Vset values we have seen. And if we talk about the practical operational amplifier, then we will be available with a limited range between these 2 points A and B. Okay? So whenever we have the voltage, difference voltage Vd in between this range AB, then it will vary linearly with the output. Okay, so we will see some linear relationship between the difference voltage and the output voltage in both the cases. After this point has been reached, what is happened? My output is going to saturate. Okay, so this is the voltage transfer curve, and we have seen this range. The range will be very much small. Okay, in previous session what we have seen is the range is around plus or minus 75 microvolt for IC741, having a gain of 2 into 10 raised to 5. Okay, so this was the voltage transfer curve, okay, where this AB represents the input range for linear operation and it is very much small. Okay, so this is what we have seen up to this. Now today we are going to discuss the characteristics of practical op-amp, and before we move on to the practical op-amp characteristics, we will be seeing the equivalent circuit of this practical operational amplifier. Okay, so generally what do you mean by this equivalent circuit? See, it is nothing but the circuit which represents the operational amplifier parameter in terms of some physical components for the analysis purpose, right? And this is what we call equivalent circuit of an operational amplifier. Okay, so now let us try to draw this equivalent circuit first. Okay. Equivalent circuit of practical operational amplifier. Okay, now we know very well that we will be available with two input. One is the inverting input and another one is the non-inverting input. Okay, so this will be my two inputs, input V1, input V2. So one is the inverting input, which is denoted by negative terminal, and another one is the non-inverting input, which is denoted by positive terminal. Okay. Now yesterday we have discussed about the ideal characteristics. Okay, so in case of ideal characteristics, we have seen that the op-amp will be called ideal if it possesses infinite input impedance, such that there will not be any loading effect. Okay, so here we need to represent one input impedance. Okay, so in between this terminal 1 and 2 there must be very high value of impedance, and we call it R in. Okay, so ideally its value should be infinite, and practically we should have very high value of this R in. Okay, then what is the next stage? Now we will be available with our differential amplifier, which will give us the output which is very much higher than this difference voltage Vd, which is equal to V1 minus V2. Okay, so now we will have one voltage source which will give us a very high amount of voltage compared to input signal. Okay, so let us try to represent this voltage source. Now what should be the value of voltage source? It is gain times the difference voltage Vd. Okay, and we will measure this voltage with respect to the ground. Okay, then we will be available with output voltage over here. Okay, so we will be measuring the output voltage across some load resistance. Let us call this load resistance as RL. Okay. So here we are measuring output voltage V0. Okay, now output voltage V0 will be decreasing if we are available with some output impedance. Okay, so ideally speaking, the output impedance should be equal to 0, but as we know, there must be a small finite value of output impedance which is denoted by R0. Okay, and in case of IC741, we have seen this typical value of output impedance, which is around 75 ohms. Okay, so this we can call a circuit diagram, equivalent circuit diagram. Okay, so here we are measuring our output voltage V0. Okay, and we will be providing positive supply voltage and negative supply voltage in this particular case. Okay, so what are these where are these components actually? Where is this R in? Where is this R0? Where is this voltage source AOL times Vd? Okay, it is under the symbol of triangle which we are using. Okay, so these entire components are below this triangle, and here we are providing positive supply voltage and VEE, negative supply voltage. Okay, so this will be our equivalent circuit of operational amplifier. Okay, and this circuit shows the operational amplifier parameters like this input resistance, output resistance, open loop voltage gain in terms of
Hello, Archan sir. Hello.
Yes. Hello. Hello. Any problem?
Archan, Tejas here.
हाँ बोलो सर.
हाँ बस कहीं नहीं एक announcement करवानी चाहिए खाली टीचर्स डे ने related.
Yes, yes, please.
Okay. So any one of you please respond. Students. Hello.
Hello.
Yes, sir.
Yes, sir.
So Teachers Day. So as you know, Teachers Day is on 5th September, right? But 5th September is Sunday, so we have planned to celebrate Teachers Day on
हाँ
6th
તમે વાત કરી કઈ.
Monday. Okay.
હલો તમે વાત
Yes,
કરી
sir.
એ ડાયરેક્ટ મારી પાસે આવ્યો એટલે મેં તમારી પાસે મૂકેલા મારો લેક્ચર ચાલતો હતો એટલે
So so
લેક્ચર ચાલે છે.
has the circular reached you?
Yes, sir.
Okay, so I hope you have gone through the circular and you know what activities the government has asked us to do, right? The conventional thing that you used to do during your school days. Okay. So few students from mechanical are coordinating this event. So if you wish to participate in the celebration of Teachers Day, I suggest that you coordinate with those mechanical students and give your if you want to participate, then give your name along with topic, or if you wish to coordinate a fun game, then you give your game description of that game to those students, right? Along with that, how many of you wish to come to college? Any one of you please count the number of students who wish to come to college for Teachers Day celebration and tell me, because as you know, due to this COVID SOP, we have to make arrangement for you to sit properly, maintaining social distance, and if there are some if there is an arrangement of fun games, then we have to make arrangement for that as well, right? And if you have gone to the circular, you know that everything has to be done by you, right? We will be there only for support everything, starting from the event anchoring, delivering lectures, coordinating fun games, everything has to be done by you. Okay, so only thing that you have to tell me is how many of you wish to come to college, right? And then for remaining things, if you want to participate, then you coordinate to the students who have posted the circular in your WhatsApp group. Okay, is the instruction clear?
Yes, sir.
Yes, sir.
Okay, thank you. Okay, thank you, Archa.
Okay, thank you. Okay, so we'll begin now. See, we were talking about this circuit diagram, the equivalent circuit diagram of practical op-amp, right? So it shows us the input resistance, output resistance, open loop voltage gain in terms of the circuit components like this R in, R0, etc. Okay, so ultimately what we are available with is this circuit, the amplifier. It amplifies the difference between the two input voltages. That is what we know. So if we talk about the output voltage V0, then V0 would be equal to AOL times VD, where VD is nothing but the difference between two input signals. So it is equal to V1 minus V2. Okay, so this is my output voltage equation, right? Let us call this equation as equation number 1. Now here you can see the output voltage is directly proportional to the difference voltage VD. Okay, so it is to be noted that the op-amp amplifies the difference voltage and not the individual input voltage. Okay, so the output polarities get decided by the polarity of this difference voltage VD. Okay, and here you can see this voltage source AOL times VD. It is nothing but the Thevenin's equivalent voltage source, while R0 is the Thevenin's equivalent resistance if we look back into the output terminals. Okay, so this equivalent circuit plays an important role in analyzing various operational amplifier applications as well as in studying the effect of feedback on the performance of the operational amplifier. Okay, so while we are going through different applications, linear applications and non-linear applications of operational amplifiers, then we will try to do the analysis, try to perform the analysis based on this equivalent circuit only. Okay, So quite simple equivalent circuit is there for the practical operational amplifier. You can see nothing is there. Just we need to consider this input resistance, output resistance, and there is one voltage source AOL times VD. Okay, that is it. Other parameters are already known to us. Okay, now let us come back to the practical op-amp characteristics. Okay, up till now whatever characteristics we have seen, this was ideal characteristics. Okay, so we are considering the ideal values of each and every parameter associated with it. Now whenever we are practically implementing the circuit, at that time whatever operational amplifier we are using, what amount of parameters are there, what will be the actual amount of the parameter, what will be the actual value of these parameters, that is what we have seen. Okay, so the characteristic of an ideal op amp can be approximated closely enough for many practical op amps, but basically the practical op amp characteristics are little bit different than the ideal op amp characteristics. Okay, so we will discuss various characteristics of practical op amp. Okay, so first we will start with the open loop gain. Okay, so it is nothing but the voltage gain of the operational amplifier when no feedback is applied. Okay, and practically the value is several thousands. Okay, this is the typical value. Several thousands, and that is what we have seen in case of IC741. The open loop gain is around 2 into 10 raised to 5. Okay, so this is the typical value of practical op amp. Then let us talk about the input impedance. Okay, now comparing this input impedance in case of ideal, then we are available with the infinite input impedance, but practically it is finite, and the typical value of this input impedance is greater than or equal to 1 mega ohm. Okay, but as we have discussed, if we use field effect transistors for the input stage, then we can further increase this value of input impedance. Okay, so in case of field effect transistors, the value is hundreds of mega ohm. Okay, so we have some finite value of input impedance. Now talking about the output impedance. Okay, output impedance was 0 in case of ideal op amp, but as we know, this is not the case with the practical op amp. Okay, so typically the value is of output impedance is few hundred ohms, and with the help of negative feedback, if we are using negative feedback, we will see what do you mean by feedback and what is the difference between the positive feedback and negative feedback. Okay, so for now, if we use the negative feedback, then we will be able to reduce this value of output impedance to a very small value like 1 or 2 ohms. Okay, so we'll be able to reduce the value of output impedance up to this extent. Only 1 or 2 ohm will appear at the end of the outputs. Right? Then talking about the next characteristics, which is nothing but the bandwidth, the range of frequencies. Okay, so bandwidth of practical op amp in open loop configuration is very small. Okay, but with the application of negative feedback, it can be increased to a desired value. Okay, so whenever we are using the operational amplifier in open loop configurations, at that time we will be limited with the range of frequencies. Okay, now what do you mean by this range of frequencies? Say if I talk about the minimum frequency and maximum frequency, and if we are operating the op amp in between this frequency range only, then it will get the desired accurate output. Okay, And whenever we are operating the op-amp out of this frequency range, then output will get distorted. Okay, it will not give us the accurate output. So for bandwidth using a negative feedback, we will be increase the range of the bandwidth to a desired value. Okay, so whenever we are performing the we will see the applications of operational amplifier, then we will consider the case of increasing this bandwidth of the practical op-amp. Okay. Then the next parameter is input offset voltage. See, whenever both the input terminals of the operational amplifiers are grounded, ideally what should be happen? What should be the value of output voltage? It should be equal to 0. But we know this not happens because the practical op-amps shows a small non-zero output voltage. Okay, and to make this output voltage 0, a small voltage in terms of millivolts or microvolts is required to be applied to one of the input terminals. Okay, so such a voltage makes the output voltage exactly equal to 0. So whatever voltage we have applied, that DC voltage which makes the output voltage 0 when the other terminal is grounded is called input offset voltage, which is denoted as VIOS. Okay. Now, how much voltage to which this terminal and with what polarity to be applied is specified by the manufacturer in the dataset. Okay. So this input offset voltage generally depends on the value of temperature. Okay. A small amount of voltage in terms of millivolt or microvolt needs to be applied to any one of the terminals. Okay, to make the output voltage equal to 0. Right? Then our next parameter is input bias current. Okay, so for ideal operational amplifier, we have seen that no current will flow into the input terminal. Okay, and the practical op-amps do have some input currents which will be very much small, say of the order of nanoamperes. Okay, the typical values of these currents are 10 raised to minus 6 ampere to 10 raised to negative 14 ampere. A very small amount of current is there. Okay, so most of the op-amp use differential amplifier as the input stage, that we know. Okay, so the two transistors of the differential amplifier must be biased correctly, but practically it is not possible to get exact matching of the two transistors. Okay, so the input terminals, which are the base terminals of the two transistors, do conduct the small DC current. Okay, so this small base current of the two transistors are nothing but the bias currents, which are denoted as IB1 and IB2. Let us try to understand this. Okay, so I am talking about the input terminals. Okay, we are available with, see, terminal 1 is grounded and input terminal 2 is also grounded, you can see. Okay, so this is my typical operational amplifier, but there will be a very small amount of current of the order of 10 raised to minus 6 ampere to 10 raised to minus 14 ampere, which will be flowing through this input terminal. Okay, so you can define the input bias current as the current flowing into each of the two input terminals when they are biased to the same voltage level. Okay, that means when our op-amp is balanced. Okay, so these two input currents when op-amp is balanced are shown in this figure as IB1 and IB2. Okay, so two bias currents are never same, hence the manufacturers specify the average value of input bias current IB, okay, which is found by adding the magnitudes of IB1 and IB2 and dividing them by the sum 2. So mathematically, if we talk about the input bias current IB, then IB is equal to IB1 plus IB2 divided by 2. Okay. So this will be the effect of input bias current. Then let us talk about input offset current. Okay. Now we have these two currents, IB1 and IB2. Okay. So the difference in the magnitudes of this IB1 and IB2 generally is called as input offset current. Okay. And this input offset current is denoted by IIOS. Okay. So now if we talk about the value of input offset current, then it is given by the difference between the two input bias current, that is IB1 minus IB2. Okay. So magnitude of this current is very small and it is generally of the order of 20 to 60 nanoamperes. Okay. And it is measured under the condition that input voltage to the op-amp is 0. Okay. So if we apply equal DC current to the two inputs, output voltage of the op-amp must be 0, but practically there exists some voltage at the output, and to make it 0, the two input currents are made to differ by small amount, and this difference is nothing but the input offset current. Okay. So both this input bias as well as input offset currents depend on the temperature. Okay. So we will be able to calculate this current according to data sheet. Okay. Suppose, say for example, I have the base current for the emitter coupled transistors of the differential amplifiers like 18 microampere and 22 microampere. Okay. These are the two base currents. Now suppose we have to find out the input bias current and input offset current for the op-amp. Okay, so what we are going to do, we are available with the values of IB1, which is equal to 18 microampere, and IB2 is 22 microampere. Okay, so input bias current IB is given by IB1 plus IB2 divided by 2, and this comes around 20 microampere. Okay, this is my first target. Second is I want to find out the input offset current. It is denoted by IIOS. Okay, so input offset current is the difference between the base currents IB1 minus IB2, and that is equal to IB1 is 18, IB2 is 22, and it is around 4 microampere. Okay, so this is how we will be able to calculate input bias current and input offset currents. Okay. So these are some practical parameters of operational amplifier. Okay. Apart from these parameters, there are some important parameters of operational amplifier. Okay. So that two other parameters are, we already know, it is the slew rate and power supply rejection ratio. Okay. Now let us discuss about these two parameters in detail. We already know what do you mean by power supply rejection ratio and what do you mean by slew rate. Okay. So first we will take on PSRR, that is power supply rejection ratio. Okay. So according to definition, the power supply rejection ratio is defined as the ratio of the change in input offset voltage due to the change in supply voltage producing it. Okay, keeping the other supply voltage constant. And we also know that it is also known as power supply sensitivity, right? So we know very well that PSRR is given by change in input offset voltage to the change in supply voltage, producing it by keeping other supply voltage constant. Okay, and same is true with the other source also. If we have a constant value of VCC, then it is given by delta V IOS by delta VCC. Okay. So talking about the value of this PSRR, okay, now we know the value of input offset voltage is very small. Okay, so if you wish to represent PSRR, then we will express it in terms of millivolt per volt or even microvolt per volt. And the typical values of VSRR in case of IC 741 is 30 microvolt per volt. Okay, this is the value of power supply rejection ratio. Now, second parameter is slew rate. Okay, so slew rate, how to define this slew rate? It is defined as the maximum rate of change of output voltage with time. Okay, so generally these slew rates are specified in volt per microsecond. Okay, so we have seen the equation of slew rate. It is nothing but dV0 by dt, and its value is maximum, the maximum rate of change of output voltage with respect to time. Okay, and this slew rate is caused due to limited charging rate of the compensating capacitor and current limiting and saturation of internal stages of operational amplifier. Okay, when a very high frequency large amplitude signal is applied. Okay, so what will happen, this internal capacitor voltage cannot change instantaneously. Okay, generally the value of this capacitor voltage is provided by dVc by dt is equal to I by C. Okay, so for large changing rate, the capacitor should be small or charging current should be large. Hence, you can say the slew rate for the op-amp whose maximum internal capacitor charging current is known, that can be obtained as S is equal to I max by C. Okay, say for example, if we talk about IC 741, right? So IC 741, the charging current is 15 microampere and internal capacitor is 30 picofarad. Okay, so what will happen to its slew rate? Its slew rate is 15 into 10 raised to minus 6 divided by 30 into 10 raised to negative 12. Okay, so it is around 0.5 volt per microsecond. Okay, so this is the amount of slew rate. Okay, now we have this much amount of slew rate for a typical operational amplifier. Okay, so what will happen? What is the effect of this much amount of slew rate? Okay, see, consider we have one operational amplifier circuit with unity gain. Okay, what do you mean by unity gain? AOL gain is equal to 1. So whatever will be the magnitude of input voltage, same will appear at the output. Okay, if my input signal is of 5 millivolt, then output voltage will also be equal to 5 millivolt. Okay, so we are considering this case, and consider that we have the input as a square wave. Okay, not the sinusoidal one, but we are applying input signal in terms of some square wave. So here is my input signal. Of a square wave. This is the maximum value, this is minimum value, and this is base. Okay. Now, if I have gain which is equal to 1, then what should be the output voltage? The output voltage should also be at the maximum value of output voltage should also be equal to plus Vm and negative Vm. That is what we have seen, right? Now, what will happen when the input is square wave? Output has to be square wave. Okay, but this is observed for certain frequency of input. Now, due to slew rate of an op-amp, for a particular input frequency, my output will get distorted. Okay, so what will happen? See, actual output should follow the input voltage waveform because we have voltage gain which is equal to 1. Okay, so my output voltage should exactly match with the input voltage waveform which we have drawn over here. Okay, so this should be my output voltage, but this is not happens because of the slew rate. Okay, because of the slew rate, what happens to output voltage is this. See, now my output voltage will be like this. Okay, you can see the output voltage is exactly not the square but some trapezoidal kind of shape we are getting. Okay, so this will be my output because of the slew rate. Okay, so this indicates the change delta V0. Okay, and this is the time delta t. Okay. So if you observe such a distorted waveform on CRO, then you will be able to obtain the slew rate as is equal to delta V0 by delta t volt per second. Okay, so the typical value of this slew rate as we have seen is 0.5 into 10 raised to 6 volt per second, or you can also call it 0.5 volt per microsecond. But what is the ideal value? The ideal value should be infinite. Okay, so higher the value of slew rate as, better will be the performance of operational amplifier. Okay, so this is the effect of slew rate on the output voltage waveform. Our output voltage waveform will get distorted. Okay, and this is to be minimized by increasing this value of slew rate. Okay. Now let us try to derive the equation of this slew rate. Okay, because as I have told you that the square wave, exact square wave of output voltage will be observed for certain frequency of input. Okay, so for a particular frequency, my output is not going to distorted, but for other frequencies our output is got distorted. Okay, so we have to find out this maximum frequency for which my output is not going to be distorted. Okay, so let us try to derive this slew rate equation now. So again we will consider unity gain operational amplifier circuit. This time we will consider sinusoidal input. Okay, so If my input is sinusoidal, definitely output is going to be sinusoidal. Okay, so let us say my input signal Vs is equal to Vm sin omega t, and output voltage equation will be same. It should be equal to Vm sin omega t. Why? Because the gain provided by the circuit is unity. Okay. Now, what is the rate of change of voltage with respect to time? So dV0 by dt is given by Vm omega cos omega t. Okay, but we know the value of S is equal to dV0 by dt, but rate is maximum. Okay, now when this rate will be maximum, if we look back at this equation, say this is my equation, okay, we will call it equation number 1, right? So this equation 1 will have maximum value when this parameter cos omega t will be equal to 1. Okay, so now what will happen? We are remaining with this Vm omega. Okay, so this dV0 by dt will be maximum when this cos omega t will be equal to 1. Okay, so we are left with this Vm omega. Okay, so this is what we require. Okay, now my S is equal to Vm times omega. And what is omega? Omega is 2 pi f. Okay, so we have this value. S is equal to 2 pi f Vm volt per second. Okay, this is the equation, required equation of slew rate. Okay, now for distortion free output, the maximum allowable input frequency, which is Fm, can be obtained as Fm equal to S upon 2 pi Vm hertz. Okay, so this is the maximum allowable frequency. Now if we go beyond these frequencies, then our output will get distorted. Otherwise we will get the exact output voltage waveform as the input signal. Okay, so this Fm is also called full power bandwidth of the op-amp. Okay, it is also termed as full power bandwidth of the op-amp. And here this Vm is nothing but the peak value of the output voltage waveforms. Okay, so these are the important parameters of operational amplifier. Okay, now let us try to solve some example based on these parameters. Okay, so we'll take on one example. Okay, I have been given one op-amp which operates as a unity gain buffer. Unity gain buffer with voltage 3 volt peak to peak, and the shape is square wave. Okay, so we have square wave input. Okay, now if op-amp is ideal, if op-amp is ideal with slew rate of 0.5 volt per microsecond, then we need to find out the maximum frequency of operation. Okay, so it is given to you that we have a unity gain operational amplifier whose input is 3 volt peak to peak square wave input. Now what we require is, whenever we are providing this 3 volt peak to peak square wave input, my output should also be equal to 3 volt peak to peak square wave. Okay, so this is 3 volt, this is negative 3 volt. Output should also be like this. Okay, but for this we must operate our operational amplifier within the stipulated frequency range. Okay, so what should be the maximum value of frequency under which my output will not get distorted? Okay, so I need to find out this frequency. Okay, and slew rate is also available to us. It is 0.5 volt per microsecond. Okay, so now we have been given value of Vm. Okay, sorry, value of peak voltage. Sorry, 3 volt peak to peak is there. Okay, okay, I have made a mistake over here. 3 volt peak to peak means this entire range is 3 volt. Okay, this entire range is 3 volt. That means half will appear, half is 1.5 will appear above the baseline and 1.5 will appear below the baseline. Okay, so the peak value Vm will be equal to peak to peak voltage divided by 2, that is 3 by 2, which is equal to 1.5 volt. Okay, and we have derived the slew rate equation. What is slew rate equation? Fm is equal to S upon 2 pi Vm. Okay, so let us use this equation to find out the maximum value of frequency. S upon 2 pi Vm. Now S is 0.5 per volt per microsecond, that is 10 raised to minus 6, 2 pi into 1.5. Okay, so upon solving this we will be able to get the value 53.051 kilohertz. Okay, so this is the maximum value of frequency up to which my output will not get distorted. If I increase the frequency to 54 kilohertz, then the effect of slew rate will be seen in the output voltage waveform. So our output voltage waveform will now get distorted. Okay, so this is what we are having. Now we need to understand some voltage, about some voltages and currents. Okay, so we have seen typical offset voltage and offset current. Okay, so we have input offset voltage, we have input offset current, we have input bias current and output offset voltage also. So what are these voltage and what are the effect of this offset voltage and offset current on the performance of the operational amplifier? So you need to understand it very well, right? So when these two transistors of the input stage are not perfectly matched, okay, and this is the usual case. See, remember, whenever we talk about the manufacturing of semiconductor devices, though the same manufacturer will manufacture the same device. If I talk about bipolar junction transistor, if I talk about field effect transistor, if we talk about IGBTs or MOSFET, though they are manufactured by same manufacturer, two transistor, two device, two semiconductor device will not be same, exactly same. Okay, so if we talk about the characteristic, then the shape of characteristics will same, but there will be a very small difference in the values of these parameters. Okay, so we will not find any two device which are exactly matched. Why? Because what we are doing in this BJTs and MOSFET, we are doping some impure materials, right? Silicon is doped. Okay, so this doping will not be exact, and this is the reason why we will not get the exactly matched characteristics in this case. Okay, and what we are doing in operational amplifier, we are using the differential amplifier as our input, where we are using the emitter bias circuits, two emitter bias circuits, which means we are available with two semiconductor devices involved in it. Okay, So these two transistors of the input stage are not perfectly matched. Then what will happen? Then the two base currents and are will be different, and there is some difference between their base emitter voltages also. And due to this, what happens? The presence of unwanted voltages and currents will be there, and this unwanted voltage and currents are called offset voltages and currents. Okay, so we need to understand the concept of offset voltages and currents very well. Okay, so we will see input offset voltage first. Okay, see, whenever both the input terminals of the operational amplifiers are grounded, ideally what should be the value of output voltage? It should be equal to 0. However, in this condition, the practical op-amp will show a very small non-zero output voltage. Okay, why? This is because the mismatching which is present in the internal circuit of operational amplifier, and such a voltage will cause some error in the practical applications for which our op-amp is used. Okay, so our necessity is to make such a voltage 0. Okay, and to make such a voltage 0, it is necessary to apply a small difference voltage between the two input terminals of operational amplifier, and that voltage is known as input offset voltage. Okay, so if we try to define the input offset voltage, then you may consider this definition: the differential voltage that must be applied between the two input terminals of an op-amp to make output voltage 0 is called input offset voltage. Okay, and it is denoted by VIOS. Okay, so let us try to understand this thing graphically. See, we have one operational amplifier circuit, okay, whose both the input terminals are grounded. That means the potential available here is 0. Okay, so difference voltage is ideally equal to 0. So what should happen to output voltage? Output voltage should also be equal to 0. But when we measure the output voltage, this output voltage will show some value. Okay, it will not indicate the 0 value. Okay, so there is some presence of output voltage, and to make this output voltage equal to 0, we need to apply some voltage to the input terminals, and that voltage is known as input offset voltage. Okay, so what I am doing now, see, my input terminal is already grounded, but I need to provide a small DC voltage. Okay, let us call it VDC1, or you may also apply a voltage to second terminal. Let us call it VDC2. Okay, now what will happen? This will make our output offset voltage equal to 0. Okay, so this VIOS is nothing but the difference between this voltage VDC1 minus VDC2. Okay, so this VIOS can be positive or negative. Hence, we need to consider absolute value of VIOS. Okay, so the smaller the value of VIOS, better is the matching of the input terminals. Okay, so this input offset voltage also depends on the temperature. Okay, so many times voltage to one of the input terminal is applied with the proper polarity so as to null the output, keeping other input terminal grounded. Okay, so for ideal op-amp, the input offset voltage is equal to 0. Hence, practical op-amp model is generally used. Okay, so the indication of practical op-amp would be like this. Okay, see, this is my ideal op-amp. Okay, you can see this is our ideal op-amp. But when we consider the practical op-amp, at that time we need to consider this small input offset voltage like this. Okay, so this will be our practical op-amp. Okay, like this. The outer one is practical op-amp and inner one is ideal op-amp. Okay, so this was the concept of input offset voltage. Similarly, we will try to understand the input offset current, input bias current thoroughly, and then we will look back to the effect of these offset voltages and currents on the performance of operational amplifier. And then we will see what are the remedies to nullify the effect of this in offset voltages and offset currents. So what are the circuit diagrams are to be used, which are known as compensation network. Okay, so we'll be looking at the compensating networks to nullify this effect of offset voltages and currents. Okay, and that we will do in next lecture. Okay, so we will stop here. If you have any doubt, then you may ask.
Excuse me, sir.
Yes.